Suppose that we have a graph, for example, this one. Some code for computing it. In particular, it's based on the statistical package R. How do we run this program? The easiest way is using the command R. Okay, this is the syntax. R, an option that is required to tell the system that you want it to exit without making questions, without saving the environment, and so on. And then, sorry, I wrote twice. You need to redirect the standard input from file PageRank.r, which is the command file that you've seen here. This is some sample lines that should help you understand what's going on where you compute the PageRank score of a graph. Here I define this adjacency matrix. Okay, graph. Rbind is a command that glues together row vectors. The vector is introduced by C and enclosed in parentheses. So here I define a matrix called the graph, a pure adjacency matrix where 1 represents the existence of a link. For example, I get the number of nodes in the graph as the length of one of its rows, for example. We want to compute the PageRank score. So we take the matrix, and as you remember, the first thing that we have to do is normalize it so that every row has a sum equal to 1. Let's build the PageRank vector, so the vector of probabilities or of prestige. In this case, okay, I create a matrix that contains a 1 in the first position, and then it repeats 0 for the remaining n minus 1. We can choose either we put a 1 in the first entry and 0 in the others, or maybe we just repeat the same value for all entries, making it a uniform vector. To apply the algorithm, we don't need this normalized matrix, but it's transpose. But transposing a matrix is very easy. You have the function T for that. So I create a new matrix TL that transposes the value of L. And then, okay, let's forget about this commented row. So this is the loop that recomputes every time the PageRank score. And we do it in a very simple way. We take, this is the matrix multiplication, okay, percent star percent. So here we are actually computing P equal to matrix product P. We do it a lot of times. So the basic iteration of PageRank is just repeating this line, okay? Applying again and again matrix, our matrix to the vector. And what we get, okay, it's this result. Okay, in this case I made 100 applications of the matrix to the vector, and I got this. You see here I printed the first iterations of the algorithm. In the first iteration, you see, actually the one that was in first position moved to the second position, which is what we expect, because the only move that the user can make from node 1 is going to node 2. And then the second move is necessarily to node 3. Subsequently, after the user is in node 3, then the probability splits between nodes 1 and 4, which is what happens here. And then it proceeds to becoming more and more complex until we get a distribution here, which is not yet the final one, because you see that from step to step it keeps changing. Actually, if I put again a 100 here, okay, now you can see that the iterations, this is the 99th iteration, this is the 100th iteration, they have more or less stabilized. They only change in the 1, 2, 3, 4, 5, 7th decimal place. Okay, this is what we do with the power iterations. So with repeating the application of the matrix to the prestige, the probability vector. But what we can do is also try to solve exactly the PageRank equation. Remember that the PageRank equation is simply P equal AP. This is an eigenvector equation that asks the system to find the eigenvector of the matrix having eigenvalue equal to 1. But in general, given the matrix A, an eigenvector is some vector where the matrix operates just by scaling it without either moving or rotating it. So it's every vector that is changed by matrix A by just extending or shortening it, where the amount of extension or shortening is called eigenvalue, and a vector that receives this treatment is called eigenvector. How can we find the vector? We can ask R to compute an eigenvalue, a spectral decomposition of the matrix by this command, eigen applied to a square matrix will try to compute all eigenvalues and all eigenvectors of the matrix. If I do it, it will return two matrices. One is the matrix of eigenvalues, and one is the matrix of eigenvectors. In this case, we are interested in the eigenvalue having value 1, which is the first. And we are particularly interested in the corresponding eigenvector, which is this first column. Okay, this first column reports the exact, meaning that it has done lots of iterations to get it, the exact value for the eigenvector. As you can see, this is not exactly the numbers that we got before. Before we got 0.125, meaning 1/8, and 0.25, meaning 1/4. Actually, if you see, element 1 is still double of element 2. So if we renormalize these values by requiring that their sum is 1, we get actually the values that we want.